4.5 is a review of stoichiometry, which we did do that in Chemistry 1. Remember that the coefficients in chemical equations represent the numbers of molecules, not the masses of the molecules. However, in lab, we do use counting by weighing to determine the molecules involved, where we use the mass, but then we can convert it to moles and convert it to molecules from there. In order to determine the amount of reactants or products involved in a chemical reaction, a mole ratio must be used. Remember that a mole ratio uses the coefficients of two molecules in a reactant that are being compared in a reaction. I think that's a typo, sorry. So to calculate the mass of them, make sure that you have a balanced equation, convert the known mass into moles, use the balanced equation to set up the mole ratio appropriately, then use the mole ratio to calculate the number of moles desired of the product or reactant that you're looking for, and then convert it back to grams. You could also do this with other parts of the mole map too, but focusing solely on grams right now. So, solid lithium hydroxide is used in space vehicles to remove exhaled carbon dioxide from the living environment by forming solid lithium carbonate and liquid water. What mass of gaseous carbon dioxide can be absorbed by 1 kilogram of lithium hydroxide? So the first thing we need to do is write our balanced equation. All right, so we have lithium hydroxide, here I'm going to write this up here, lithium hydroxide solid is reacting with the carbon dioxide that's exhaled, so the CO2 gas, to form the solid lithium carbonate. Carbonate has a -2 charge, don't forget about that, and water vapor. So after you write the equation, you want to make sure that it's balanced, and I see my lithiums are not, so if I put a 2 there, that makes 2 O's plus 2 is 4 O's. Okay, we have a total of 4. I think that makes it balanced. Awesome. Okay, so now we know we have 1 kilogram of the LiOH, lithium hydroxide, and we want to know the mass of gaseous carbon dioxide. And since mass, I'm just going to convert it to grams. They don't say kilograms, so let's just do grams, one less step. Okay, so we have kilograms to start with the lithium hydroxide though, so we're going to have to convert that. So we have 1 kilogram of LiOH over 1 is our starting point. So there are 1,000 grams in 1 gram, or 1 kilogram, excuse me. Okay, now we can then go with our normal converting. So to get it to be moles, we divide by molar mass, and we're dealing with the LiOH right now. So the molar mass of LiOH, I found it to be 23.948 grams of LiOH. Okay, now after we get to the moles of LiOH, now we need to switch moles. This is where that mole ratio comes in, okay? So it's moles 1 over moles half. Using the coefficients in front, we want the CO2, we have the LiOH, so it's going to be 1 mole of CO2, because there's a coefficient of 1 in front of there, over 2 moles of LiOH. Okay? Then we need grams, we need a mass, so we would multiply by the molar mass of what we want, which is the CO2, and I find that molar mass to be 44.00915. Okay, so when you solve, I got that to be 918.8 grams, so 3 significant figures would be 919 grams of CO2. Okay, we have used mole ratios, we have done this already this year, I'm pretty sure, in a little bit in Unit 1, but it's nice to remind ourselves how to do it. Based on the ingredients available, only so many sandwiches can be made when you buy packages from the store. So how does this relate to chemistry? This relates to chemistry in the limiting reactant. So you can only make, in this picture, there's bread, meat, and cheese, and you can only make so many sandwich ratios, and you're going to have some stuff left over. And those leftover pieces we could call excess reactants. So consider the reaction between gaseous nitrogen and hydrogen to form gaseous ammonia. So in this model, we were just talking about models, weren't we? We have H2, we have N2, we have NH3. If we were to write the balanced equation, we would see reacting both of those together to make ammonia. To balance it, we would need to put a 2 there and a 3 there. That's like kind of weird, 3, sorry. So for every one N2 molecule, we need 3 H2 molecules to make 2 NH3s. So if you look at how it's grouped together in this picture, they've grouped it that way, where you have 3 H2s with 1 N2 on the reactant side before the reaction, and then all of those turn into 2 NH3s. So when it all works out perfectly in the relative amounts, it's called a stoichiometric mixture, where the numbers of reactants, or the amount of reactants, matches the balanced chemical equation, moles or coefficients. But what if there aren't equal amounts? So in this situation, we still have grouped together our 3 and 2, or 3 and 1, but then there's some leftover N2. There's some leftover nitrogen. So these nitrogens, we were trying to get to this before with our models. This is leftover reactant. It's not a product. You wouldn't write it on the product side of the equation, so that is still leftover reactant. And so when we have leftover reactant, then we have to get into our limiting reactant. So if we have leftover nitrogen, that means the hydrogen limited the reaction. So when it ran out, it's all used up, it's consumed, there's none left over. Okay? To determine how much product can be formed from a given mixture, we have to look at the reactant that is limiting, the one that runs out first. So a reactant that runs out first and thus limits the amount of products that can be formed is called the limiting reactant. We have done this in Chemistry 1. We have done this, I think, this year, but let's practice it just again, just to be sure. Nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. So we're going to have ammonia go with the copper 2 oxide. The other products of the reaction, so that must mean that nitrogen gas is a product, is solid copper, that's a product, and water vapor is a product. If a sample containing 18.1 grams of ammonia is reacted with 90.4 grams of copper 2 oxide, which is the limiting reactant, how many grams of nitrogen will be formed? All right, first thing to do, write our balanced equation. So we are reacting ammonia, which was just in our last picture, NH3, plus copper 2 oxide. So copper has a +2, oxide has a -2, so that's just CuO, to form nitrogen gas, copper metal, and water vapor. I'm saving time by not putting states of matter. You go for it if you want to. Okay, let's balance this. Well, I'm going to balance the nitrogens first by putting a 2 there. That makes 6 H's, so I need a 3 here. That makes 3 oxygens, so 3 and then 3 coppers. Okay. So we want to know the limiting reactant, LR for limiting reactant, and we want to know the grams of nitrogen formed. So we want to know the mass of the nitrogen gas. Okay? And we are given that we have 18.1 grams of NH3 ammonia and 90.4 grams of copper 2 oxide. Okay, so remember, with limiting reactants, you keep the 2 values separated and solve for each them simultaneously, and then you pick up the lower of the 2 tells you the limiting reactant. Okay, so we're going to have to solve everything for NH3's value starting point and for the CuO starting point. So 18.1 grams of ammonia over 1. Divide by molar mass of ammonia. And that is 17.031 grams of NH3. Okay, then we are going to do a mole ratio. Well, it's 1/2. Remember, we want the N2, so that's 1 mole of N2 over, we're talking about NH3 here, so 2 moles of NH3. Now you could pause here and just solve for moles, and then when you compare the moles, then take only one of them further, or you could just keep going, and I prefer actually just to keep going myself, but it's up to you if you would like to pause and then go. So I'm going to go, and then to do that, you just multiply by the molar mass of N2, which is 28.014. Now, solving that out and rounding to some correct significant figures, you would get 14.9 grams of N2. That may or may not be the answer. We have to do the same exact thing for the CuO, 90.4 grams. And then we'll decide which is which. Okay, so now the process is the same. Not all the numbers will be the same though. Okay, so we're going to divide by molar mass, but this time we have to divide by the molar mass of the CuO, which that is 79.539 grams. Then our mole ratio, the numerator will be the same, 1 mole of N2, because we still want N2. But the denominator this time, we're dealing with CuO, so we need 3 moles of CuO in the denominator. And then the very last step is going to be exactly the same, because we still are solving for grams of N2. So we use the molar mass of N2. Okay? When you solve that out, I got 10.6 grams of N2. Okay, now we have to answer 2 questions. We need to know the limiting reactant, and we need to know what's the maximum amount of mass. So the limiting reactant goes hand in hand with the maximum amount. Now, when it says maximum, it's not what you think. It's not going to be the 14.9, because it's going to be the lower of the 2. Because when you run out of one of the reactants, it's going to stop the process. So you're going to stop making, so you won't make as much. Okay? So the correct answer is the lower of the 2 numbers for the nitrogen gas. So that's 10.6 grams. And then that tells us that the limiting reactant is the one that created it, which is the CuO, the copper 2 oxide. Okay? So the copper 2 oxide produced less N2, so that means we must run out of the copper 2 oxide first. Okay? So that's just a review of limiting reactants. The amount of a product formed when the limiting reactant is completely consumed is called the theoretical yield. The actual yield of the product is often given as a percentage called the percent yield. We've used this equation before, but I didn't want to just solve with this equation. I wanted to throw one in that you're going to see in the homework problems, so you have a good idea of what to do with this. Because in Chem 1, we just solved for the percent yield, and yeah, that's great. But that's not really what happens in industry, so we want to make it related to that. Oh, don't forget that the maximum amount of nitrogen that can be produced to form the quantities of reactants used is this theoretical yield. Sorry, I skipped that. Okay, phosphorus can be prepared from calcium phosphate by the following reaction. Phosphorite is a mineral that contains the calcium phosphate plus other non-phosphorus containing compounds. What's the maximum amount of phosphorus, that's the P4, that can be produced from 1 kilogram of phosphorite if the phosphorite sample is 75% calcium phosphate by mass? So if we have 1 kilogram of the phosphorite, this is saying that only 75% of it is actually the calcium phosphate, which is a part of our reaction. Okay, so we have to just use this percentage to help us get on our way. Okay, so let me just, I'm not going to rewrite the equation since you have it right there above you, but we're going to start with our 1 kilogram of the phosphorate, and I'm just going to put phosp. I hope that you know what I mean when I say 1 kilogram of phosphorite. Okay, now our percentage was 75% calcium phosphate, Well, I already know that I need to convert it to grams to go to moles to go back to grams. So I'm going to go ahead and multiply by 100 or by 1,000 grams to get it to be in grams. Okay, so grams over kilograms. Now, this is where we have to switch it from grams of the phosphorite to grams of the calcium phosphate, which is technically what's in our equation. And how you do that, so if it's 75%, if you had 100 grams, 75 of those 100 grams would be calcium phosphate. Okay, so again, this is if you have, if 100 grams is your sample, 75 grams would be the calcium phosphate. So what we're going to do with that is we're going to use that as a ratio to cancel grams of phosphorite and be left with grams of calcium phosphate. So we're going to cancel the grams of phosphorite, so we need to put the 100 grams, the total grams of phosphorite on the bottom, and we would put our 75 grams of the calcium phosphate in the numerator. Okay, so then now we can then go on as planned. So it's just a little bit extra work to get to where we need to go. So at this point, we then will divide by the molar mass of the calcium phosphate, and that is 310.18. If you don't get that yourself, you are having trouble with molar mass. So ask me for help, please. Then the mole ratio, and this is looking back at this equation. So we want this, and we have this, so it's going to be a 1 to 2 ratio. 1 mole of P4 over 2 moles of the calcium phosphate. And last but not least, we need to convert it to grams of the P4. And yes, you do need to use the subscript of 4, so multiplying phosphorus times 4 gives you 123.896 grams of P4 over 1 mole of P4. Okay, now, so you could have like paused here and then solved and then kept going, but I just tried to fit it all in one. So when you solve, the final answer is 149.79 grams of phosphorus P4, and we need 2 significant figures here, so 150 grams is fine, or you could say 1.5 times 10 to the second. Either one of those is good. Okay, so again, just to review, if you're ever given like a percentage in a problem, then you just have to set up the ratio, and it's either going to be 100 grams over the percent, like 75 over 100 or 100 over 75. I think there might be a homework problem where it might be 100 over 75, and it just has to do with canceling units, so just be careful with that. Okay. To wrap it up, in Unit 1 we covered the principles of, chemical stoichiometry a little bit. These same principles will apply when you have solutions, but 2 points to consider. It's difficult to immediately tell what the reaction will occur when 2 solutions are mixed. And it's also, oh yeah, I'm just getting ahead of myself, guys. We want to convert all quantities to moles at all times, but it's good practice to think about the reactants and ions involved in the reaction. Also, it's important to obtain the moles of the reactants. So we might need to use molarity, like in Unit 3, moles over liters equals molarity. Okay, so we have this example 7 that just kind of throws it all in one. So calculate the mass of solid sodium chloride that must be added to 1.5 liters of a 0.1 molar silver nitrate solution to precipitate all the silver ions in the form of silver chloride. Well, we have solid sodium chloride reacting with aqueous silver nitrate solution, and it's precipitating to silver chloride, solid, and then by process of elimination and double replacement rules, our other product will be sodium nitrate. And solubility rules tell us that's most likely going to be aqueous. Okay, so that's a 1-to-1 ratio all around, which is nice. So we want to know the mass of the sodium chloride that's needed to be added to convert all of the ions into silver chloride. And we know that we have 1.5 liters of a 0.1 molar silver nitrate solution. Okay, so there's two ways to do this. You could do your molarity equals moles over liters, solve for moles, and then go mole ratio and then go grams. But I like parentheses, so I'm going to do it where I'm going to start with my volume of the silver nitrate, and then I'm going to multiply by the molarity, which I know that's moles over liters, so I'm going to say it's 0.1 moles of silver nitrate over 1 liter of silver nitrate. So then see how I'm getting rid of liters of silver nitrate there? Okay, and then from here we just jump right into the mole ratio. So it's a 1-to-1 ratio, like I said before, so 1 mole of sodium chloride over 1 mole of the silver nitrate. And then now we have moles of sodium chloride, so then we can go to grams of sodium chloride by multiplying by the molar mass of that. And then when you get it, the correct answer is 8.77 grams of sodium chloride. Okay, so this is just another option of how you can combine different ways of solving using stoichiometry. Last but not least, we in Unit 3 talked about gas laws. So you can use the ideal gas law. We did this a little bit. The PV equals nRT, or molar volume. Remember, molar volume is 22.4 liters in every 1 mole. Those could also be used to determine amounts as well. And we did do that a little bit in Unit 3, so we're not going to extend this video by trying any of those. If you do have trouble with this, check out page 161 in your textbook. There is a list of what you can do to help you follow these steps in order to solve these problems. Okay, so if you're struggling with stoichiometry, look there first since I'm not going to be here, and then ask me questions.